Hi there, I'm Luke McKinney, Course Cram's Physics 117 and 118 instructor. In this video, we're looking at projectile motion, a special two-dimensional case of the equations of motion.
Now, projectile motion comes up all the time, and that's brilliant for you because it's basically double marks, because it's doing equations of motion all over again. The difference is equations of motion is in one dimension. Projectile motion uses two dimensions, but each of them is separate. So we're basically getting double marks for doing the same thing twice. Now, the basic idea of projectile motion, you have something, you launch it at some launch velocity at an angle, and then it flies in a parabola through the air until it hits the ground or something else. Now, young people are all very used to this with Angry Birds, but of course, us older, wiser people like me are used to it from Worms, which was a much better game a long time ago. But either way, we deal with this shape, the parabola, and there's a couple of properties about it which are useful. The first is that it's symmetric. So it takes just as long to go up as it does to go down. So if it takes 10 seconds to rise that height, it'll take 10 seconds to fall down. It's also symmetric if the launch speed at this point was 20 meters per second, then at the same height over here, the speed would again be 20 meters per second. And a little bit of revision, you can see that's the same speed, the same size of number, but it's a different velocity because it's a different vector, a different direction. It's going down instead of up. And another little useful property we'll use later, at the top there, the vertical velocity for an instant is 0 meters per second because it's not going up or down anymore. It was going up before, which is in the plus y direction. It's going down afterwards in the minus y direction because in physics, plus and minus are just directions. And we're going to plug all of these into the equations of motion. Now, how do we do that? Well, we look at it again. Remember, if you try to do two things on one diagram, you don't get anything much done. The key is when this is going in two dimensions, we have the x dimension horizontally and the y dimension vertically. And the key is there is no acceleration usually in the x dimension, unless they mention something like the projectile has a rocket motor or something, and you wouldn't miss that. In the y dimension, the acceleration is minus g. So it's minus 9.8 meters per second squared. So for our object flying through the air, it always has an acceleration down of minus g, so that's minus 9.8 meters per second squared. And we'll see now how to fit that into our equations of motion. The first thing we do is break the problem up into our two dimensions, x and y. We've got an object with a launch velocity at some angle to the horizontal. And we can break that up into x and y using trigonometry, which sounds like a very long word, but something we'll use a lot in this course. We'll turn it up later in forces and momentum and all sorts of stuff. We just have our right triangle. The horizontal component is the velocity times the cosine of the angle. And the vertical component, the launch vertical component, is the launch velocity times the sine of the angle. And those are the values that we use for our equations of motion. Now you'll notice again what I did there. I said the launch horizontal component is the launch velocity times the cosine of the angle. I didn't say Vox equals V0 cos theta, because that sounds like a serial number or some sort of override code, which isn't really how our brains work. So always remember to say the letters as we move on. And now we'll plug those in to the equation. So starting with our equations of motion in x, the new horizontal velocity is the launch horizontal velocity plus the horizontal acceleration times time. But we know that horizontal acceleration is 0. So that's just the launch horizontal velocity, which we've already worked out. You'd always write out the full thing though, because if it's a long answer question, you don't want to miss marks for the equation. And if there is a rocket motor or something added to the problem, you'll instantly know, oh, hey, that's where I plugged that in. Then we want to know, how far do things go? Well, how far do things go horizontally? The change in position is the launch velocity times time, plus a half the horizontal acceleration times time squared. Again, that acceleration is 0, and we can plug in the new position minus the old position. Never forget to include that. Sometimes the object will be launched from 10 meters, and you don't want to get your answer wrong, is equal to the horizontal launch velocity times time. So we need the time, and no time like the present to look at that, ho-ho. That'll just come from the y dimension. Now, how can we use that? Well, what happens at this time? This time is when our projectile hits the ground again. So the new height is 0. Or maybe we're asked, when does it hit a 10-meter tall platform? So at that point, the new height is 10 meters. Either way, we know what the new height will be. So we have an equation we can plug that into, which is the change in y is the launch y component times time, plus a half the vertical acceleration times time squared. So the new height minus the launch height is equal to the launch velocity times time, plus a half minus g times time squared. And now we have an equation with only one unknown. Once we plug in the new height, the old height, the angle, the launch velocity, and g equals 9.8, remember, then we can find the time. And then once you have the time, you plug that back into x to find the horizontal range. So very often in a problem like this, you'd actually do the vertical first. You don't worry about that too much. It's not a big thing to memorize, but once you've done a couple of problems and you find, oh, hey, I always need this value, then you start doing that value. And then the next thing you know, you've got a couple of extra minutes in the exam because you didn't have to go back and forth. There's also another nice little shortcut. Sometimes in problems you're asked to find the maximum height. How high does it go? So we want to find out about when it's here. Well, remember, as we said in equations of motion, sometimes numbers you need are encoded in the question in the words. And we've already seen something about this. Whenever they say it's at the highest point, that means it's the new height here, where for an instant, the vertical velocity is 0. And we want a distance, not a time, which might ring some bells in your memory. And if not, don't worry, we're about to do it again. Remember, there's an equation of motion which only cares about distance and doesn't care about time. So we plug in the values for that. So the new velocity, which is 0 at the highest point, is equal to the launch velocity, vertical component, plus twice the acceleration, minus 9.8, times the change in height, the new height, minus the launch height. And again, it's one of those things that looks like a bit of an Euler equation, but when you plug in the numbers, then it's just calculator work, and you can get the final answer there. Final little useful note, if you fire these things around, how do you get the furthest range? How do you get to go as far as possible? Well, since there's no air resistance in any of these problems, you get the furthest range when the launch angle is 45 degrees. Again, not a big, scary deal, but just sometimes that has occasionally been asked, so I mention it, and now you can answer it.
Well, I hope that video was useful. What's even more useful is more videos, and you'll find plenty more in the playlists here. But even more useful than that would be a live session with lots of focused practice, the ability to answer your questions, and then doing lots of exam-style practice with focused example problems and full solutions. Because that's what we do at Prep 101. So make sure to join our Prep 101 Study Hub Facebook page, where you'll get details about all the sessions, some of them are even free sometimes, and other resources that'll help you to do better on your exam.